Welcome to another Tech Tuesday. Today is Tuesday, and we're doing an IAEI Live, but I am recording this session, and I'll tell you why. I'm in Charleston, South Carolina, in a hotel room, as you can tell, and I am basically here for the duration. So we have the first draft meetings of NEC 2026. So we're reviewing this week all of the public inputs associated that were made associated with the 2026 edition of NFPA 70, which is the National Electrical Code. So it's going to be a very busy 2 weeks. The first week I have Code Panel 2 meetings because I'm on 2. I represent NEMA on Panel 2. And then on the second week, I represent Eaton on Code Making Panel 10. So I have to be here both weeks. I will be talking to Panel 12 and I think hopefully Panel 7. I sent an email to the chair of Panel 7 to address Panel 7 in regard to marinas and electric boats. Now, what we learned was the initial issue that was raised to me on electric boats, because we don't have any code requirements around we have electric vehicles, which does not include a boat. So we have no input with regard to how do we address electric boats and charging of electric boats. So 625 does not apply because it only applies to electric vehicles, and vehicles does not include a vessel that floats. So in any case, that's how our journey started, and we expanded that because we learned that 625 doesn't apply to a lot of other types of electric vehicles as well. So the thought process is to create a new article. But again, that's the thought process. We could combine everything into 625, change the title. I don't know which way the panel is going to go. All I know is I'm presenting the issue and a possible solution, and we'll see what comes out of it. But I want to make sure Panel 7 is aware of what's going on in Panel 12. So, because it directly impacts their requirements. Now, so I am going to I'm recording this session for IAEI News Live, and hopefully that's okay, because on Tuesday we will be I'll be working through lunch because task group works. You know, as we're going through the panel public inputs and we're creating first revisions and panel statements, in many cases, we have working lunches and even working evenings. So suffice it to say, we will be, I'm recording this one. So thank you for joining in. Today, I want to focus this. Now, last week, was it last week? No, 2 weeks ago, we journeyed into transformers. And remember, transformer discussions, we had the protection of the transformer. We had clearly identified that Article 450, yeah, 430's motors. 450 Article, man, I tell you, the numbers rolling into each other. So we clearly identified that the Article 4 transformers, 450, only applies to transformers. So just like in Article 430 only applies to motors, motor control circuits, and controllers, 450 only applies to transformers. And then we learned that the primary and secondary conductors are feeders. So because they're feeders, you have to follow the rules in 215, which then points you straight over to 240, and follow the general rules for protecting a feeder conductor. So now what I'd love to do is move over to Article 445 for generators, because and so in our discussions last week, when we did last week's session on Article 215 feeders. I thought that was appropriate because we were already in that area because of our discussions around transformers. But then I believe even during that call, we started to talk about power source output conductors. That sort of got us over to 690 and 705 a little bit. But then generators came up, and I thought, I don't believe that I have covered a generator before for an IEI News Live, and I'm not sure if I did or not, but I've got a lot of videos out there. But I thought, you know what, since have our mind set in and around these feeders, and I know the conductors coming from a generator, the output of a generator are feeders. They're not service conductors. I don't go to Article 230 for those. Because they're feeders, I'm again in Article 215. So I want to cover generators. So this discussion is going to be a sort of a look at 445. We'll take a look at what the requirements are in 445. But I also want to take a look at some terms, defined terms, because we have to understand the fact that the output conductors from a generator is a feeder and it's not a service. So I want to have that discussion. And then I'd like to take a look at some of the protection and what are the requirements in 445? What do we have to do to protect generators, their output conductors? And then obviously we're probably going to have a transfer switch. We're going to talk a little bit about separately derived systems versus non-separately derived systems. We'll chat about that a bit as well. All right. Without further ado, let's talk about generators. But first, let's go to definitions. Now, my code book is in my truck. And quite frankly, I wanted to make sure I recorded this because everybody's coming in right now. It is Sunday. And I know I had a long breakfast chatting. We're catching up. I'm seeing people I haven't seen in so long. So had a long breakfast, lasted until from 8 o'clock to 12. I came up here. I don't even know what time it is right now. It can't be 9:41. It's going on 1 o'clock. So I want to make sure I record this session. So I don't have my code books, but when you don't have your code book, you know what? NFPA link is the place to go. So I do have NFPA link. Now, I want to take a look at the definition of service and service conductors. Make sure you got your spectacles because you are going to need them. So let's take a look at service and service conductors. LMNOP, QRS. There's service drop. Okay. First, let's talk service. The definition of service is the conductors and equipment connecting the serving utility to the wiring system of the premises served. An on-site generator is not a utility. So that equipment, when you feed the generator to, say, a transfer switch, or if you were putting that generator in, putting a load on the generator, that equipment is not service equipment. Service conductors are the conductors from the service point to the service disconnecting means. So if I have a generator going to a transfer switch, that cannot be service conductors because the service point is not in that transfer switch. So those conductors from a generator are not service conductors. That's not required to be, unless the transfer switch is listed as service equipment, and now the equipment is service equipment, but on the normal side, you're going to connect to the service point, right? So that's the transfer switch. That's not the generator. So we know the generator typically comes with a breaker, but not all the time, right? So if I don't have a circuit breaker on the generator, and say I'm paralleling generators or whatnot, then I don't have a circuit breaker on the generator. Those are still feeders because the generator is a source. Now let's go look at the definition of a feeder. And I know we talked about it last week as well, but you know what? I've learned about definitions. You can never read definitions enough. So a feeder, look at feeder. all circuit conductors between the service equipment, the source of a separately derived system or other power supply source, and the final branch circuit overcurrent device. Now, we know that the generator is at least an other power supply source. So we know that much to be true. So now the question is it a separately derived system or not? We're going to get into that discussion as well. What is a separately derived system? Well, we're still in Article 100, and we're going to take a look for the definition of separately derived system. There it is. I can't give you a page number because I'm on NFPA link. An electrical power supply output other than a service having no direct connections to circuit conductors of any other electrical source other than those established by grounding and bonding connections. So, that's a very important piece of the puzzle, because if I think of, and I'm going to try something here. See, I don't have my mouse, and I'm going to go to Me Teach. Hey, it worked. All right, without a mouse, without a whatever. Continuity camera. Okay, so let's draw this out. So I have, we'll call this the transfer switch. And here, and here, and here. I almost want to make a smiley face. All right, so, and we will do the conductors. Ooh, what do we want to do the conductors? We'll do the conductors in black. How about that? All right, so I come off of this, and let's say that whoops. This goes down to, we'll say a panel board, right? We'll just do this. Panel. All right, so up here I have utility. And I would typically come through a overcurrent device. And then I would have a feeder breaker connected to my transfer switch. Then over here, I have a generator. And I would typically have a breaker there and connect that to my transfer switch. So if I lose my utility, and let's say I do this, I'm normally on my utility side, and if I lose my utility, then that moves over. I'll just dotted line this one. How about that, huh? That moves over to the generator. And typically what will happen is you'll tell the generator to start, and then you'll transfer. Now, I have coming off of here, I have 3 hots and a neutral and an EGC. Now this transfer switch can be a 3-pole, taking out the 3 hots, or it can be a 4-pole. Now, and also in this equipment, let's just do this. I want to be in here. I have a neutral bus and I have an equipment grounding bus, and I have a neutral bus, which I can't draw a white on white, can I? So we'll just say this is my neutral and this is my equipment grounding. Now, off of this, I will make sure that I bond these two together. in my service equipment. I'm bonding the neutral and the equipment grounding, and I come off of this and I go to the earth, and then I also bond my equipment. Let's do it this way. Boom. I'll show it to the outside of the box. So I have all of this going on here. My neutral and my equipment grounding, everything is bonded and combined together. If I'm only switching 3 poles, if I look back at the definition, it says everything has to be separate except for the equipment grounding. So let's just draw the equipment grounding. I know that I have a bond going between that enclosure and that enclosure. And let's say that this generator, this is all together. I am bonded. I bond the generator equipment with the transfer switch, and then I'm bonding the downstream panels, and all of my bonding has to occur as per Article 250. So all of my bonding is consistent to all of the different pieces of equipment. And my neutral, now what happens to my neutral? Let's pick a color for neutral. Ooh, how about gray? Will gray show up? Let's try it. So if I have a neutral coming, if I have a neutral, if I have my neutral coming in and I'm not switching it, then my neutral just basically passes through and passes down to this equipment with my hot. Right? So, and then up here, so I'll have a neutral point. I'll also have a ground. So this is my ground. I make sure that I tie my I make sure that my neutral, so this is neutral, and this is ground. Now, do I have a rod out there? Sometimes you will see a connection to ground. All right, and what we'll do is we'll draw that this way. If I am not switching the neutral, I have to make sure that there is no bond between the two. So what do I know? One, if not a 4-pole, and I'll say I'll say not switching the neutral. If not switching neutral, make sure you separate the equipment grounding, EGC, from neutral at the generator. Now, why is that? Now, some generators may ship bonded, and you have to take a look in the generator to see and look at the instructions that come with the generator to determine whether or not there is a bonding going on. And if you have a 3-pole transfer switch and it's bonded and you drove a rod, for whatever reason, there's no code requirement that says you have to drive a rod at that generator if it's a non-separately derived system. You have a 3-pole transfer switch, that generator is a non-separately derived system because the neutral is common. If I'm breaking the neutral, so let's say that I do this, I'm breaking the neutral. All right? So now I'm switching the neutral. So along with the hot conductors, I'm also switching that neutral conductor. Now, when I switch over, now the neutral And all of this bonding that occurred over in the service equipment is no longer a part of the system. Now you have to make sure that you have a bond between the equipment grounding and the ground rod that you drove out there at the generator and your neutral in the generator. And that would mean you have a 4-pole generator, or a 4-pole transfer switch that is switching that 4th pole, which is the neutral. The three, so if this is a 3-phase, the 3 hots and the neutral. If it's single phase, it would be a 3-pole instead of a 2-pole, right? That's why I just said I eliminated the poles. I said not switching the neutral. If you're not switching the neutral, then that generator is not separately derived because the neutral is common between both systems. And you're relying on the grounding in your service equipment for that bond and ground for the system, for that grounded conductor. If you're switching the neutral, then the generator is a separately derived system. And now you have to derive the bonding in the generator between your grounded conductor, your neutral, your grounding conductors, and your grounding electrode conductor. Okay, so you have your grounding conductor, your grounded conductor, and your grounding why did I draw an E for a G? Your grounding electrode conductor, right? So your EGC, your GEC, and your neutral, for the lack of a better word, your grounded conductor, all are bonded in the generator. But don't do that bonding if you're only going to have a 3-pole switch. All right, so I was out at a job site and we were doing an inspection. So we open up the generator and I look inside and I can see the ground rod that's basically was underneath the generator. They must have driven the ground rod, drove the, put the generator on top and then did all of the grounding and bonding. Well, I noticed that there was a connection between the equipment grounding, the grounding electrode conductor that was connected to that rod and to a terminal strip. And that terminal strip, there was a jumper that bonded with the neutral. And then we went into another building and then there was a transfer switch, but it was a 3-pole transfer switch, not a 4-pole transfer switch. So the inspector said, hey, I'm going to flag this because they're not switching the neutral and they're bonded out there. So now I've got 2 grounds. Right? I've got a grounding electrode out there and bonded to neutral, and that same neutral conductor is also bonded and grounded in the service panel board. So now I can have circulating currents, etc. So instead, all I told him that all we needed to do is basically, and he was thinking, well, we're going to need to buy a new transfer switch. They're going to have to buy a 4-pole transfer switch. When in reality, all they needed to do, and which is what they did, was disconnect the bond between the neutral and the ground inside the generator. It's okay to drive a rod for a generator and bond it for whatever reason you think you want that. It's not a code requirement, but you can. And then I pulled up the instructions for that generator. For the generator, it was, I can't remember what brand it was. But I learned in the instructions, it says, if this is not a separately derived system, then remove the bonding strap. And there were instructions and diagrams on exactly what to remove. And it was perfect. So the manufacturer of that generator did a great job in their instructions. And all we had to do was basically say, look, do I have a 4-pole or a 3-pole? Am I switching the neutral? Am I not switching the neutral? If I'm not switching the neutral, then it's a non-separately derived system. If I'm switching the neutral, then it is a separately derived system, and I need to be bonded and grounded in that generator. Make sense? So that's why it's really important to understand separately derived systems and non-separately derived systems, and make sure that you have the grounding and the bonding all being performed or done in the right locations. So, let me do this. So there's my filter in and out. Let me go to map and come down this way. All right, so now what I want to do is I want to take a look at the I want to take a look at the 445, right? All right, I'm just doing a quick look. I can see where that generator was, but I don't have the images because I believe I took them with a different computer. All right, so let's take a look at, let me bring up my webpage, bring up NFPA link. So we talked a little bit about separately derived versus non-separately derived. We know that the conductors from the generator, whether or not they're protected, if you have an overcurrent device in the generator or not, I don't really care. They're feeders because they meet the definition of feeders. So we know we're going to be going to 215 and 240 for their protection. We know it's not service equipment. We know we could have a separately derived system or a non-separately derived system, depending upon the bonding that occurs in the generator and the transfer switch. Both of those two have to match, and I hope you understand why. So now let's take a look at 445. I think we're ready to go to 445. So 445 is titled. Now, again, I'm going to be using NFPA link. I'm in the 2023 code edition. I know that sometimes some states do not adopt, and you might be on an older code edition, but in my opinion, not too much has changed in 445. So 445, the scope is installation and other requirements for generators. And when they say other requirements, I think they mean the fact that what you'll find in 445, there's a lot of requirements that are about the construction of generators, because I don't believe that some generators are required to be listed. In fact, 445.6 says stationary generators shall be listed. So if it's not a stationary generator, or if it's of a kind or custom manufactured generator, then you can field. So if it's not a stationary, you're not required to be listed. If it is stationary, it's required to be listed. But if you have a one-of-a-kind or a custom generator, custom manufactured for whatever reason, you can field label it. So remember, a field labeled is saying that you would have a field evaluation body that would come out and review the generator. And that's just reviewing the generator. That's not necessarily reviewing the installation, because you have a custom built generator. And those are permitted to be field labeled. So that's going to be looked at by a field evaluation body, which is a defined term again. And that's just the way that is. Location generators shall be of a type suitable for the locations in which they are installed. They shall also meet the requirements of motors in 430.14. Now, if we look at 430.14, 430.14 deals with, and so you have to be mindful. Generators are, if you have, like, say, a diesel generator, a gasoline generator, whatever, the fuel is very important, and you have to think about the ventilation and the contents of the fuel, etc., that are basically turning the generator, the prime mover, so to speak. So In 430.14, they talk about motors shall be located so that adequate ventilation is provided so that maintenance, such as lubrication of bearings and replacing of brushes, can be readily accomplished. Well, you're going to be doing similar things. Motors and generators are very similar to each other. You think about it. I have a rotor and a stator. If I am driving the rotor, the stator is my generator. And I'm rotating the rotor, I'm turning it via some prime mover. Now, if that prime mover is a diesel engine, well, can you put a diesel engine indoors? You're going to have the exhaust from the diesel engine. You're going to have fuel for the diesel engine. You've got to think about placement of the generator in its entirety, all the different parts and pieces. And now, is it possible to put a generator indoors? I've seen it done. Believe it or not, it was a residential dwelling unit. It was a very large home for a very rich individual, whoever it was. They had a humongous generator in the basement in a special area. It was concrete. It had special ventilation fans and a whole bit. They spent a lot of money to put the generator inside the structure. Is it possible? I'm going to say heck yes, because I've seen it done legally. It is very expensive because you have to address all of those concerns and issues around not just the rotor and stator, but the prime mover, whatever is turning that rotor. You've got to consider it as well. So it points you back to 430.14 from a location perspective. There's an informational note. NFPA 37, standard for the installation and use of stationary combustion engines and gas turbines. So that's more information on the location of generators. So NFPA 37 is going to be another reference for you as well from a location perspective. Now, again, you've got to think about the exhaust. Remember, technically, if I would say a generator from an electrical perspective doesn't necessarily include whatever's turning it, because whatever's turning that generator could be many different things. It could be water, right? You could have a dam and the water from the upper reservoir passing through pipes, gaining momentum and gaining speed, hitting a turbine could turn the rotor. I can have steam. I can boil that water and take the steam and turn the turbine, which turns the rotor. I could take a nuclear reaction and boil water and turn a turbine based upon the steam. There's a lot of different things that I can use to turn the rotor of a generator. That is there's just so many different ways, but you have to think about the entire picture. Because if I would say, well, am I going to put the generator in the basement? Well, okay, or in this area, yes. Well, the prime mover comes with it too. The whatever that engine is comes with it. So all of it has to be able to be installed in that area. And I'm glad it points us to NFPA 37, because NFPA 37 probably does a much more extensive review of all the different types of technologies and whatnot. Well, you know what? Here, this is NFPA Link. Here's what I'm going to do. I'm going to open a new window, and we're going to go and we're going to come down to the bottom and view all publications, type in 37 and enter. Look at that, NFPA 37. And because I pay my monthly rate for the NFPA Link, I have access to 37. So then I go to reference publications, definitions, engines, engine locations. Let's take a look. 4.1. This is engine locations. Engines shall be situated so that they are readily accessible for maintenance, repair, and firefighting. Looks like that was a recent change. The air supply shall be designed to meet at least the minimum requirements for combustion, cooling, and ventilation, and to prevent flue gas products from being drawn from stacks of flues of boilers or other combustion devices. Combustible materials shall not be stored in the rooms. Remember that I remember that place, the dwelling unit that had that generator in the basement. That was the only thing in that room, and it was completely encased in concrete. All four walls, the ceiling, and the floor were all concrete, and they had specific locations where they had the ventilation and everything. Engines fueled by a Class 1 or by liquid phase LP gas shall not be installed in rooms containing fire equipment or open flames. And then combustion air filters mounted directly on engine or turbines shall be listed in accordance with UL 900. Now point you to another standard. Engines located in structures, engine rooms located within structures shall have interior walls, floors, ceilings of at least 1 hour fire resistant rating. And then it points you to 41212 for other reasons. So you've got to think about the fire rating and the containment of if something goes wrong with that generator. You don't want it to burn the structure down. So in any case, there is a lot of information in NFPA 37 to help guide you in where you're going to place your generator. Marking requirements. Now, so when we get into, so here's one of my, I say, it's not a complaint. It's, I don't know if I'd call it I'm not going to call it a complaint. I'm just going to say, look, here's another thing about 445. There are requirements in 445 that are basically standards driven. But again, not all generators are required to be listed. So now stationary generators are, but not all other generators. Now, you have a marking requirement, and I could argue that if you put anything in this marking that is a part of a nameplate of a generator, that should automatically be done as long as it's listed. But let's take a look at what the requirements are for markings and see, are they a part of the listing? Should it be there as part of the listing, or is this something you add after the fact? We need our spectacles. Now, the other thing I like about NFPA Link is I can make the letters bigger. I can't do that in my code book. Each generator has to be provided with an accessible nameplate, giving the manufacturer's name, rated frequency, the number of phases, if it's AC, the rating in kilowatts, kilovolt amperes, or kilovolt amperes, power factor, the normal volts, the abnormal volts, the normal volts, and amperes corresponding to the rating and the rated ambient temperature. So that's information that as long as you have a listed product, that's going to be there. Nameplates or manufacturer's instructions shall provide the following information for all stationary generators and portable generators rated more than 15 kilowatts. Alternator, subtransient, transient, synchronous, and zero sequence reactances. Now that's one of the, and I'll tell you, well, let me give, there's 5 things you need. I'll tell you what that first one means, but so you need the subtransient, transient, synchronous reactors. You also need the power rating category, prime, standby, or continuous. And that's important too. That's important to tell you how it's basically going to be used. Is it always going to be running? Is it going to be relied on temporarily? Because what they'll do, if it's always relied on, if you say this is going to always be on for extended periods of time, they're going to derate some things from a generator perspective, because you got to think about the heat. If it's only going to be used for short periods of time whenever you lose power or whatever, then you'll probably have a little bit larger. You can adjust the kVA rating of that generator, the output, because you're not going to be running it for an extended period of time. So just keep that in mind. Alternator temperature rise. Indication of the generator is if the generator is protected against overloads by inherent design. So in some cases, you can have generators that are protected inherently from overloads. And that's important to know. If you don't have, say you're paralleling generators and you have generators that do not have breakers inside, there probably is some overload protection that gives you some freedom in regard to the protection of those output conductors, those feeders from the generator. And there are requirements in 445 that deal with that. So alternator, okay, indication of generator is protected against overloads or by inherent design or an overcurrent protective relay or a circuit breaker or a fuse. Available fault current for inverter-based generators in lieu of the synchronous, subtransient, and transient reactances. Those reactance values are what we use to calculate fault currents at different periods of time. So when you think about how do we model a generator, what you will typically see is a generator, you'll see this, an inductor, and then a resistor as your output. Now, this impedance, this combined impedance, is what we use to calculate fault current on the secondary at the leads of that generator. To represent, I'll make sure I say this right. Think about a waveform. So let's do it this way. There we go. So if we think about a fault current waveform, you're going to have, it follows what we call as a DC offset, and that will be determined by the X to R ratio. And your fault current will do this. So it has an asymmetrical slope down. And your generator output will do the same thing. Now, how do we calculate, say, this first half cycle, right? The first half cycle, and then maybe the next cycle or two, and then, the rest of it. How we calculate those numbers are based upon those parameters that we mentioned earlier. The subtransient reactance, the transient reactance. Let me find that again. I know the subtransient reactance, the transient reactance, and synchronous reactance. Those are your three. So your subtransient reactance, that is that first half cycle. That is a very low impedance. It will give you a very high fault current value because we know that is going to be a peak value. Then you have the transient reactance, which is the next few cycles. And then you have the synchronous reactance, which is sort of, look, you've had the fault and you haven't cleared it after many cycles. That's sort of that decayed down as it balances around the x-axis, okay? So we use difference impedance values to represent the fault delivering capability of that generator based upon duration of fault. The initial half cycle is going to be worst, and then it decays. And then the zero sequence currents, that is what we call, will blow your mind here. You're going to go, what? What did he say? Symmetrical components. So in the symmetrical component world, symmetrical components the concept of symmetrical components was created by C.L. Fortescue way long time ago. He wrote an IEEE paper and published it and brought that to the world. And it was a way to take balanced systems and separate them into different sequences so that we can accurately calculate fault currents and other important values. Positive sequence, negative sequence so positive sequence, say, goes clockwise, negative sequence goes counterclockwise, and they're all separated by 45 degrees, right? So you have three phases, and they're equal, separated from each other. And then you have positive sequence. Oh, man, I'm going to do this. I know this is like, you guys are like, what the heck is he talking about? but I'm just giving you some background. So if I drew my sequence diagrams, I would have, okay, all 120, 120, 120, and they would be E phase, and they would say rotate this way. Negative sequence, you have the same thing. These are vectors, 120, 120, 120. It rotates this way. And zero sequence, they're all in phase with each other. So what the math tells us is if I add an angle at a negative 120 plus an angle of a positive 120, then they're going to all cancel zeros. So I basically separate my system into positive, negative, and zero, and I calculate fault currents. Your three-phase bolted fault current value is positive sequence. This is positive sequence. This is negative sequence. And this is zero sequence. That's why you'll see zero sequence. You'll see the term, but you probably have no idea what they're talking about. Zero sequence currents are all in phase with each other. That's why they will not flow through a delta. If you have a delta Y ground transformer, ground faults on the secondary do not show up on the primary. They'll show up as a phase-to-phase fault on the primary, but not zero sequence. So if you have a zero sequence relay on the primary of a delta Y ground transformer, and you have a ground fault on the secondary of that transformer, it's not going to trip because it will not see a difference, because it will be all positive. There will be no zero sequence currents. The zero sequence CT will not detect zero sequence currents on the primary of a delta Y ground transformer because zero sequence currents will not flow through a delta. They just circulate in the delta. Probably TMI, but in any case, we use the zero sequence impedance model to calculate ground fault currents. And that's why that information is required to be on the nameplate. If you are into power systems analysis and you are looking at protecting generators, you need to know what the negative sequence currents are. You might need to put negative sequence relays on that generator because negative sequence currents in a generator generate heat, like eddy currents. They will generate heat, and that can destroy a generator. So the bigger the generators get, the bigger the motors get. You'll have specific relays to protect your investment. You want to determine when that big piece of equipment is going to fault earlier. You'll put temperature sensors, RTDs, inside of the windings of motors and transformers and generators, because you want more information to detect failures early, because you may be able to rewind the motor and fix it or fix the generator. So there are protection levels that you will spend money on, or not, maybe not you, maybe the owner and the designer may say, look, we're going to put more protection on this generator because you spent a couple $1 million on it, and we can rewind it for a few $100,000 as opposed to replace it for another couple $1 million. You know what I'm saying? So the requirement in the code is to give you information, or give somebody information to help them maybe apply special relaying to provide certain protection. So you need that data. That's why it says greater than 15 kW. That seems to be the line of demarcation. If you get to these larger generators greater than 15 kW, it says rated more than, so more than 15 kW, then you're into these additional markings. All right. Overcurrent protection. So now we get into overcurrent. So now we have 5 different first level subdivisions. You have constant voltage generators. Except AC generator exciters shall be protected from overload by inherent design, circuit breakers, fuses, protective relays, or other identified overcurrent protective means suitable for the conditions of use. Remember, we're talking about the generator being protected, not the feeder conductors. We have 2-wire generators shall be permitted to have overcurrent protection on one conductor only if the overcurrent device is actuated by the entire current generated other than the current in the shunt field, and it can't open the shunt field. 65 volts or less generators operating at 65 volts or less and driven by individual motors shall be considered as protected by the overcurrent device protecting the motor. Again, it's 65 volts. So, and remember how generators work. So if I shut down that motor, if I protect the motor from overheating, etc., when the generators are delivering not more than 150% of their full load rated current. They have balancer sets, 2-wire DC generators used in conjunction with balancer sets to obtain neutral points for 3-wire systems shall be equipped with overcurrent devices that disconnect. This is shall be equipped with. This is more in the standard in the manufacture of the generator, which was my earlier point. If you have a listed generator, if it's employing balancer sets, if it's employing these things, then it's going to be a part of the listing. It's not something that you're going to do in the field. And I would say if it's listed, you're not going to be in there looking at the balancing set, because remember what Article 90 and 110 tells you. You're not going to be, if you have a listed piece of equipment, unless you think it's been modified, you're not in there looking at 445 and trying to enforce 445 on a listed piece of equipment. You're going to follow the manufacturer's instructions, and you are going to apply the code appropriately. And then they have 3-wire direct current generators. So in my opinion, from an overcurrent protective perspective, you've got to understand, is there a breaker in there? If there's a breaker in there, then you know how to size your feeders. If there's no breaker in there, then now you've got to figure out, how do I size my feeders, right? Because there's no protection at the source. Now, what's the length of my conductor? How for the terminations, just like in a transformer, secondary conductors. I don't have protection at the point of where I connect to that transformer. So now I'm into 240 transformer secondary conductors. I'm into the a specific length and how I need to protect those conductors, all that jazz. 445.13 is your ampacity of conductors. The ampacity of the conductors from the generator output terminals to the first distribution device containing overcurrent protection shall not be less than 115% of the nameplate current rating of the generator. Now, typically that's going to be internal wiring. It shall be permitted to size the neutral conductors in accordance with 220.61. Conductors that must carry ground fault currents shall not be smaller than required by 250.30a. And neutral conductors of DC generators that must carry ground fault currents shall not be smaller than the minimum required size of the largest conductor. All right, so that gives us some of the rules on protecting the conductors, sizing or determining the ampacity of the conductors. Now, B in this 445.13b talks about overcurrent protection. Now, where the generator set is equipped with listed overcurrent protected device, so that would be like your generator with a breaker installed, or a combination of current transformer and overcurrent relay conductors shall be permitted to be tapped from the load side of the protected terminals in accordance with 240.21b. And tapped conductors shall not be permitted for portable generators rated 15 kW or less. So where the generator set is equipped with a listed overcurrent protected device or a combination of a current transformer and relay, conductors shall be permitted to be tapped from the load side of the protected terminals. Protected terminals. So I can use the feeder tap rules. That's what it's doing. It's pointing me to 240.21b, which are your feeder tap rules. So I can use the feeder tap rules at that point. That's good to know. Then you have protection of live parts. Then you have guards for attendance. You have bushing requirements. You have generator terminal housings. Oh, disconnecting means. Let's talk about the disconnect. 445.18. Generators other than cord and plug portable generators shall have one or more disconnecting means. Each disconnecting means has to be simultaneously open to all associated ungrounded conductors Each disconnecting means shall be lockable open in accordance with 110.25. That doesn't mean that if you have a disconnect that's also can be locked in the closed position, that doesn't apply. You just have to be able to lock it in the open position. Now, there was some new text in the 2023 code. The disconnecting means shall be permitted to be located within the generator behind a hinged cover, door, or enclosure panel. Where the generator disconnecting means is located as such, you have to have a label to tell you where that disconnect is. And I believe that is on some of those stationary generators that you'll find on dwelling units. I believe they have a disconnect that's a part of that, and there's a little door that you can open, and there's a disconnect in there that will disconnect that generator from the structure. So I think that is providing that provision. So you don't have to put another disconnect in addition to that one. You just have to label it correctly, let people know there is a disconnect built in. Now, if you have generators in parallel, where a generator is installed in parallel with other generators, remember in some cases, you're not going to have overcurrent protection in that case, or say circuit breakers built in. The provisions of 445.18a shall be capable of isolating the generator output terminals from the paralleling system bus. The disconnecting means shall not be required to be located at the generator. Okay. You have the emergency shutdown of the prime mover. That's your emergency. So remember what we did on emergency disconnects. We put some requirements for dwelling units for emergency disconnects. And then they said, well, wait a second. What if I have photovoltaics? We didn't have to put an emergency disconnect in on PV because there's the rapid shutdown system that's already there. What about energy storage? So we have an emergency disconnect on energy storage systems. And then we said, what about generators? And now we have a requirement for emergency shutdown of the prime mover in 445.19. So all of the sources of power for first responders can be turned off. Remote emergency shutdown for other than one and two family dwelling units, generators with greater than 15 kW rating shall be provided with a remote emergency stop to shut down the prime mover. That's, I think they rearranged this section as well and added some new requirements. You have emergency shutdown in one and two family dwelling units for other than cord and plug connected portable generators. An emergency shutdown device shall be located outside the dwelling unit at a readily accessible location and shall also meet the requirements of 445.19A1 and 2. A1 is be equipped with provisions to disable all prime mover start control circuits, and A2 is initiate a shutdown mechanism that requires a mechanical reset. And then an emergency shutdown device mounted on the exterior of the generator enclosure shall be permitted to satisfy the requirements of this section. The shutdown device shall be marked as the generator emergency shutdown. That goes back to that other discussion that we just had, that in some cases these generators have a disconnect built in. And as long as we label it correctly and we raise awareness of that disconnect, you can use that for a couple things now. One, to meet the requirement for the disconnect of the generator in general, and then boom, for the emergency disconnect. You're going to have to label it, though, as an emergency disconnect. All right. Ground fault circuit interrupter protection for receptacles on 15 kW or smaller portable generators. I know this was highly debated, and well, you know where it ended up. There were a lot of people that did not want to see this go in, but it went in for portable and smaller generators. So that receptacle needs to have GFCI protection. And I think, is that the last one? Is that the last? GFCI, yeah, that's 44. Oh, no, that's it. 445.20. And then here they talk about floating neutral generators and bonded neutral generators. So you have two requirements there. All right. Agree? I guess that is all of the requirements. So there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sections in 445 for protection of that generator. And we know what the requirements are. We know we have to have a disconnect. We know that those are feeder conductors on the output of that generator, and we just have to protect those based upon for feeder protection. And because you have a breaker inside for most cases, pretty much, I don't know about you, but all the generators I've seen all have a circuit breaker installed, or they'll have some sort of overcurrent protection as part of that generator. You just have to make sure I'm protecting those conductors appropriately, the feeder conductors. So, and we know that we can tap some of those, we can use the tap rules for those secondary conductors as well. So, we spent about an hour talking about generators and a little bit more. So hopefully we got something out of this discussion. Remember, this week is NEC 2026 code cycle. We're down in Charleston, South Carolina, and all next week and the week after, it's going to be nothing but code, code, code. So stay tuned. I apologize for having to record this one, but I will probably have to record next week's. But what I might do for next week is try to grab some IAEI members and sit down, set up the tripod, and just record a discussion amongst the crew. All right, so stay tuned for that. Maybe next week we might, if I'm lucky enough, be able to grab a few IAEI members and record a session. All right, everybody, I'm done. It's the least I could do. That's all I could do. I've got to get back and get some work done. So on to preparing for this week's discussions. Thanks for watching. Thanks for taking out some time of your day to stay with us on IAEI News Live. I appreciate everything. Remember, stay safe, and please stay healthy. See you next week.